Everyone, June the 5th. Alright, let's finish this first. And I thought about this last night. I had a new idea. So we'll try it, the new idea. Check if it is a straight line. You're given an array where x, y. Check if these points make a straight line in the xy plane. How many are we talking about? 1,000. No duplicates. Is there an easier way? Nah, and I think I'm just gonna do pairwise, right? These two, these two, these two, these two, these two, and check for their slope. Yeah, let's check for their slope. Okay, we can say for k shall equal to coordinates 1, 0 minus coordinates 0, 0. I think convention is y divided by x, so it will be 1 on 1 divided by coordinates 1, 0 minus coordinates 0, 0. Okay, that's the k. Then we say for I in range 1 to len coordinates minus 1, new k shall equal to coordinates I plus 1, 1, just copy and paste. And then this will be I plus 1, this will be I, this is I plus 1, and this is I. If master is close, k and a new k. If not, turn false. Otherwise, just keep going. Nah, I don't even need to get a new k. Alright, and then at the end, we'll return true. That shall be enough. Let's give it a shot. I think is close shall be good enough. Oopsie doozy. God. Oh, special case, huh? Division by 0. Okay, so what we shall do is, gosh. If this else master.inf, same thing, this minus this. I probably should do something new k. If else master.inf. That's done. Yeah, the edge case is when 2 points are have the same x chord. I fell for that. Damn. Slope. Hey, you can do multiply. Ah, that's how, yeah. Multiply is better, and you don't have to worry about. Yep. Nah, it's not really brush up. You didn't realize that's basically what it is. I can avoid division. All right, so back on this. So what I realize is, what do we want, right? We want to make sure we can pick K cheese for the first mouse to go through. So we want to make sure that the pick, right, will result in the maximum gain between the two rewards. So what we need to do is to sort them, not based on the size, but based on the amount of advantage. So the amount of reward 1 minus reward 2. So that's what we're supposed to do. We'll do this. Actually, I like to do it this way. We will sort them by top 0 minus top 1. This is the amount of advantage that we can do by choosing reward 1. And of course, we want reverse equal to true. Well, man, we don't need to reverse equal to true. We just need to say minus and plus, right? So we do that. Then we just take the first K. That's it. We just take the first K, right? And then, so we can say sum 1, and then for I in range K, we take the first K, sum 1 plus equal to R1, R2, I0. This is R1, R2, I1. And once we're done, let's see if this is right. Yeah, you see? So when you think about it this way, it's not that hard. You just need to sort them by the advantage. Sort them by the advantage. Oh, we got it. All right, so that's all we need. Just sort by the advantage. Yeah, we should not sort by the size of reward 1 or reward 2. We shall sort by the advantage we can get by taking reward 1 over reward 2. We shall take the K largest, the K cheese, K types of cheese that grant us the max advantage of taking reward 1 over reward 2. The advantage can be computed by the difference between R1 and R2. Thus, we sort based on, we sort in reverse based on R1 minus R2. Then we just take the first k. Right, then we just take the first k, R1, take first the k rewards from reward 1, and take the remaining from reward 2. Yeah, that's that. It's not hard. It's just yesterday wasn't clear. Thought about this during the sleep. Yep, k largest, exactly. Priority queue. The hell is this? What the hell is this? Oh, dude, you don't even have... Oh my goodness. Oh my goodness. Yeah, you just need to solve... Oh my god. Okay, so two things need to... First, what the hell is this? Is a new Python thing? No, it's Panda. What is n largest? What the hell is this n largest thing? Oh, is that heap queue? Oh yeah, I think it's heap. I think it is heap. Oh, damn. Return a list with the n largest elements from the dataset, defined by iterable. Oh my god. This is the next level. Surely this is the next level. Okay, so what do? We will return sum reward 2 plus, yeah, I don't even need to do this, plus sum, when you import heap queue, right? Import heap queue, sum heap queue dot n largest, k largest, and then we say for this thing, you probably cannot do it this way. Oh yeah, of course. Damn it, man. It's minus. Oh. Oh. So not only it's also good implementation. Yeah, you can't beat that. This is a wonderful implementation. Two things to note. One, we don't have to sum separately sum 1 and rem2 as in solution 0, solution 1, because by summing r1 minus r2 we already have sum 1 minus rem2. 2, we can use heap queue dot n largest to directly find the first k, or find the k largest, r1 minus r2. Bravo. This is too good, man. This is too good. And it's a one-liner. Jesus. Can you believe that? Can you believe that? I cannot. Doesn't matter. Runtime is not important in this case, because it just does not matter. It was so good. Oh, wow. All right. What's this one? Only 19% passing. Minimum reverse operations. You're given an integer n and an integer p in a range representing a zero-indexed array of length n where all positions are set to zeros, except position p, which is set to 1. You're also given an integer array band containing some positions from the array. For the ith position in band, array that equals 0 and band I is not equal to p. So the band is not going to be 0. That's basically it. You can perform multiple operations on the array. In operation, you can choose a subarray with size k and reverse the subarray. However, the 1 in array should never go to any of the positions in band. In other words, after each operation, array band I remains 0. Return an array answer where for each I from this, answer I is the minimum number of reverse operations needed to bring the 1 to position I in array, or -1 if it is impossible. What? I have to read again. Okay, so all positions are set to 0 except for 1, okay? And then we have band, so the band position will always have to be 0. And it can perform a subarray of k and reverse the value. However, the 1 in array should never go to a band position. So you can reverse, and what if it gets, hold on, you reverse it, okay? So does the 1 disappear if you reverse and the 1 lands in one of the band position? Does it disappear? I guess if it always disappears, then it's impossible, right? Return an answer array. Answer I is the minimum number of reverse operations needed to bring I to position I. The values are independent of all i's. Just take a look at the question itself. Okay, so n equals 4. So what do we have? Let's get a draw. Ah, Lord. Hold on. My pen is not right. Okay, got it working again. All right, so we have the first one is n equal to 4, okay? 0, 1, 2, 0, 1, 2, 3. And p is 0, so this is 1. Everybody is 0. And band is this and this. K is equal to 4. So every time we can only take a subarray of size this and then do reverse. So we do reverse. So 3. So this is 0, yes. This will never get. I mean, the positions where it's band will never get 1. So they will always be 9 against 1. And this we need to 1 operation. So 1 operation put, so this is 1. Okay, number 2. Let's just work some of the examples. 1, 2, 3, 4. Okay, 0, 1, 2, 3, 4. P, so this is 1, and the band is going to be where 2 and 4 is band, and K equal to 3. So every 3 we can do reverse. Okay, so now the question, 0 is 0, right? So the question is, so this is going to be 0, this we don't know, this is going to be -1, this we don't know, this is going to be -1. So the question is, can we get to 1? So if we want 1 to land on this, right, and our K is 3, and this currently is not 1, which means to land on this, the 1 must be appearing here, right? If 1 appearing here, we reverse. If 1 does not appear in this position, you can never get to this. Okay, so for this one to work, I need this one to work. Okay, now for this one to work, I need this one to work. So now it's an infinite recursion, so it's impossible. Why you examples all -1? I hate examples they give, because the good examples you probably can figure it out by just doing the examples. 0, 1, 2, 3. P is 2, so this is 1. These are zeros. And band is 0. Jesus, this is useless. This is useless. Okay, so if you have, doesn't matter, you have a 1 here, right? The other is all 0. And you have some position band. Then if you want to move this to another position, because of the K, so what are the K? K is smaller than N. All values in. So we can only move, let's say if K is equal to 1. K is equal to 1. Then you cannot move, right? Because the subarray of size 1, right? It's the subarray of size K. A subarray of size 1 is by itself. So if K is 1, then yeah, there's no way to go. A K is 2, right? Now you can have these, you have these, so you can go here, you can go here, and from here you can go here, you can go like many different places. Now if you think about it, the K basically decides on where you can go. If we think about this as a graph, then we have the root, right? This is basically the root. And the K determines who your children are. And oh, it's not even a graph, it's a tree, right? So you have the root, and then you have, okay, so these are where you can put the 1 on. So you have a left or a right, you have 2 nodes, and from that node you can keep going, right? But you can also go back. But why would you go back? So you keep going, or you can now go, or you can keep going. Let's say that you keep going, and each one you can, yeah, if you start from a position, oh, hold a second. It just says size K, a several size K. So if I have a size 3, I don't have to, man. I do not have to do this. I can do this. I mean, of course, do this. Size 3 is useless, but if we say the size is 4, right? Size 4, we can do this, size 4, or we can do this, size 4. Dude, now this one can move here. Oh. Okay. Now that is interesting. But basically what it says, what it means is, if we have a 1 position here, right? Can we move to this position? Well, we can do 2. 3 we cannot. 4, yes, we can do on 4. If we have 4. But Oh, it depends on where it is, right? To move to the next position. How about 5? Yeah, let's say we have a very long, okay? Doesn't matter. So in this case, if I reverse it, which means we go 0, 1, 0, 0, 0, right? So we can move here. But what if I choose this? Then we say 0, 0. Huh. You can't. Wait, is this always true? What if I choose this? Then, hold a second. So what you're saying is, even an odd k would have different impact. If it's an even number, okay, it's an even number. So it's an even number. Yeah, let's do 6. 1, 2, 3, 4, 5. Even number. If one is here, you can do it here. If right, and then if one is here, then you move in here. If one is here, you move in here. Yeah, so if it's even number, we can move to the opposite, opposite, opposite. Right? If it's odd number, that's a 7. One, 2, 3, 4, 5, 6, 7. 1 we can do 1. 1 we can do 1. 1 we can do 1. So the middle will be left empty. Yeah, depending on where you put the value. Okay. So I'm given an array. I know the positions that we cannot land, which just means those positions, we cannot use those positions. Those positions are just, dead to us. So for each position, right? Or, can we, given the starting position, okay? Given the starting position, can we find all possible next positions based on where it is? Yeah, so we have an array, and in it we have a 1, right? We have a 1. Now its position, depending on how many are surrounding it. We can say, right? We can say, let's say we make this as the first one. We count if we can count k value on the other one, so we know one of the other one can be k, right? And we can now this one be the second one. Then if it's the second one, yeah, hold on. So if it's here, then this one can be 1. Then we can shift the whole thing to the left, right? We shift the whole thing to the left. Now this is the second one. Now if it's the second one, then this can be 1, which means this can be 1. Yeah, because in here is this. And then we shift to the left. We shift to the left. and this, right? And then we shift more to the left. Okay, now we shift more to the left. So we have 2 here, then we have this. And so we're gonna 1, 2, 3. So it's this one. This. And we can shift even more. Shift even more. What's shift even more look like? So we'll have 1, 2, 3, 4. This is the 4th one. 1, 2, 3, 4, 5, 6, 7. So if I'm here, this is the 4th. And it's useless because we shall only have 3. Because if you have a 4, you're in the middle. Which means if k is odd, right? And we put, if we have here, then these are all the ones we can set. These are all the ones we can set. Cannot set the one right next to it, but we can set, which means if k is 3, we can set here. If k is 5, we can set this, and we can set this, and that's it. Because we can shift 1, right? Because we can shift 1. Right, we say this is 1, then we do reverse, this will be 1. This is 1, 1, 1. Yeah, that's it. So this is when k is odd. Okay. If we have enough. But every time we can only hit one of them, right? But what if k is even? Okay, so again, 1, we can shift here, and then we shift 1. So now 1 is here. Then, oh, it's the same. Then we shift to 1 more. It'll be this one. Ooh, that is ugly. Not how I imagine it to be, but I guess it makes sense. So if it's even, damn, if it's even, we can hit this and then this. That's even. Even situation, this, this, and this. Or even situation can be like this. Okay. So now what? Now we have a starting position. Can we figure out what the next can be? I think I mean, depending on how, if you're in an array, okay, and you have a position as 1, if you have enough, the best scenario, right, you have enough on here, enough on here, then you can just lay out everything. So those next round, right, those are the next round. What if it's not enough? What if this is in the middle? What if this is in the middle? Or, you know what? You know what? Might actually be better just we set this to be the starting one, right? And then we try to see if it's enough. If it's not enough, we move until we have like this to be k, okay? And based on this, we can calculate which one can be, and that will become in a queue, okay? That will become the queue. Put this one in, and then we move the whole window left. I don't like to move the window left. Okay, that's fine. We can, put the window here, right? And then we move the window right to one position. We get another one, move one, until we can now move that we put a queue. So these are what can hit in the next round. And if they hit one of the position that's not banned, then all the better, right? All the better. If it does hit the one banned, then that would just don't get into the queue. Now from those positions, we'll do exactly the same thing again, right? We'll do the same thing again. But that's how you time out, right? Because every single one, you have to go through K. Every single one, you have to go through K. Isn't that what's going to be? Right? Every time you go through K, because you have to move like all K steps to find out where the next one is going to be, and then move another K step to find out where the next one is going to be. But maybe it will work. I can see a lot of repeated computation. Yeah, if I have one level, I have a lot of positions. That can be one. And each one we need to go K. I don't know, man. I want to think about it. Yeah, I kind of don't have any gana to do this anymore. Well, we'll end it here. Let's pick this back up tomorrow.